Greetings, physics enthusiasts. Welcome back to AP Physics 1, Unit 5, Lesson 2. And remember, please, that Unit 5 in the AP course is about momentum. And in Lesson 1, we did some algebra and we derived what momentum is. So we derived the impulse momentum theorem. We said force times time, the product of the strength of the force and the duration of the force is equal to the change in this product mv. So the product mv at the end minus the product mv at the beginning is the change. Change is always final minus initial. And this product, force times time, is called impulse. This product, mass times velocity, is called momentum. So a short way of saying that is impulse is equal to change in momentum. And we use the letter P for momentum because although momentum starts with M, we've already abbreviated a lot of other things with the letter M. All right, so that is a review from the last video. Now, what we are going to say is that momentum is conserved. So an object can be at rest, and then later on that object could be moving. So the momentum was not conserved for this one object. But the idea is that if an object is not moving and then all of a sudden it is moving, if it gained momentum, it must have been at the expense of some other object that lost momentum. Momentum doesn't just appear or disappear, it goes somewhere. So if this object isn't moving and it gained momentum, maybe there was some other object that was moving to the right and hit it and slowed down. So if this object loses momentum, it can give the momentum here. So the total momentum will be conserved, even though individual objects might not have their momentum conserved. Just like in the way if I have a green wallet and a purple wallet, and I take a $5 bill out of my green wallet and put it into my purple wallet. Well, the money in the green wallet was not conserved. The money in the purple wallet was not conserved, but the money in my wallets was conserved. It just moved from one place to the other, but the total money in the two wallets remained constant. And of course, if I have two wallets, one's going to be purple and one's going to be green, right? Because you know me. All right. So momentum is conserved. That is called the law of conservation of momentum. And I'm going to show you that it really, really is true. I'm going to derive that from you. And we are going to start with Newton's third law. So we're going to start here with Newton's third law, and we're going to use that to prove that momentum is conserved, to prove the law of conservation of momentum. So do you remember Newton's third law? Do you remember which one was the third law? That was the action-reaction thing. If A pushes B, B also pushes A. Not only does B push A, but B pushes A with exactly the same number of newtons as A pushes B with, and in exactly 180-degree opposite directions. So if A pushes B that way, B pushes A the opposite direction, same size force. So let's see what that means and how that might relate to momentum. Let's make a graph. I love graphs. Let's make a graph of force as a function of time. We usually think of force as a function of position, but let's graph force here on the vertical axis and time on the horizontal axis. Let's just make a graph that looks like this. We start out with some non-zero force, and that force stays constant, and then it increases, and then it decreases, and then we stop. So we start here at t equals 0, and we end here at some other time. Now this is some force A pushing B. If A pushes B, does B push A? Yes. What do you think the graph, if this is the graph of A pushes B, can you make a graph, maybe in a different color, of what B pushes A would look like on here? Feel free to put it on pause if you want to work, but I'm going to show you the answer. If A pushes B this hard, B pushes A with the same number of newtons of force, but in the opposite direction. So I'm going to put it down here. And this force remains constant for a while, so this force should remain constant. And then as this force increases in size or magnitude, this force will increase and then decrease and end up like this. And isn't there beautiful symmetry there? I almost got it right. But this graph should be a perfect reflection of this one, reflected across this axis. That's what Newton's third law says. If A pushes B, then this graph is B pushes A. Right? Now, that's very complicated in general. Let's think about this as if we just have constant forces. So let's think about it this way. I've got some constant force, A pushing B, for some amount of time. And while that happens, I've got the same size, opposite sign force, B pushing A for a certain amount of time. Let's see what happens there. And if from that, I can get the law of conservation of momentum. Let's do it a couple ways. First of all, just generally, do you remember this other graph? Force as a function of position, F versus X. Do you remember that graph? And we said that the area under that graph, the area under the curve, was equal to, do you remember it? It's very, very important. Area was equal to work done by this force on some object. And force times distance is work. So what do you think I'm going to say here? What do you think I'm going to say about this purple area? The area is going to equal impulse, which is the change in B's momentum. The change in B's momentum is the impulse here. What is this going to be? Well, area between the graph and the horizontal axis. It's again going to be impulse. And remember, impulse equals change in momentum. So this is the impulse or the change in momentum. A is getting pushed. So this area is the change in momentum of A. This area is the change in momentum of B, because B is getting pushed. And do you see that these two areas have the same size, but opposite signs? So what I want to say is A1, the purple area, and A2, the green area, are equal in size, but opposite in sign. So if this area was 5 and this area was -5, I wouldn't say 5 equals -5. I would say 5 equals the opposite of -5. So because of Newton's third law told us that if I have this first purple graph, then this second green graph must exist and look this way. That was Newton's third law. And then we said, hey, well, if the area is impulse, the change in momentum of B, and this area is impulse, the change in momentum of A, then those two changes in momentum must be equal and opposite. So what I'm going to say is, if I've got two objects, delta P of object 1 and delta P of object 2. If I have two objects pushing on each other in a Newton's third law kind of way, the change in momentum of the two must be the same size, must be the same number of kilograms times meters per second, but must be opposite in sign. One will have an increase in momentum, the other will have a decrease in momentum. Just like my two wallets, the green wallet and the purple wallet. Well, if I take money out of the green wallet, that had a decrease of $5. And if I put it into the purple wallet, that will have an increase of $5. So I'll take those two things, the -5 and the 5, and I'll set them equal to each other. But of course, -5 and 5 have the same size, but not the same sign. So I have to throw a minus sign in. That's what's going on. Now, let's see how this relates. Delta. Delta P1 is P1 final minus P1 initial. Delta means change, final minus initial. Equals the opposite of delta P2. P2 final minus P2 initial. You see it? Now, what I'm going to do is I'm going to replace P momentum with MV. So again, having this name momentum, helped me in writing this really compactly, but let's spread it out. So momentum MV, momentum 1, so that's the mass of object 1, the velocity of object 1, final, M1V1 final, minus the momentum MV of object 1, mass 1, velocity 1, initial. So I've got M1V1 final minus M1V1 initial equals P2. That's MV2 final minus P2 MV2 initial at the beginning. You see it? I'm going to keep the left side the way it is. M1V1 final minus M1V1 initial equals, and I'm going to distribute this minus sign. So now this is going to be negative, and negative is going to be positive. Negative M2V2 final plus negative is positive. M2V2 initial. And now what I'm going to do is I'm going to move the negative things to the other side. I'm going to move this one over here so it becomes positive, and I'm going to move this one over here so it becomes positive. So I've got M1V1 final, that was already here, and I'm going to take this M2V2 final, and when I move it to the left, it too becomes positive. I'm going to take this M1V1 initial and put it on the right, M1V1 initial, so now it's positive. And keep M2V2 initial on the right because it's still, it's already positive, M2V2 initial. Now, the final thing I'm going to do is I'm going to take all this initial stuff and move it to the left, and all this final stuff and move it to the right, just so I've got initial first and final second. In other words, if A equals B, then B equals A. You might remember that from your math class. That is called the symmetric property of equality. If A equals B, then B equals A. So I'm going to take this stuff on the right and put it on the left. M1V1 initial plus M2V2 initial equals, and the stuff on the left and put it on the right. M1V1 final plus M2V2 final. This is my law of conservation of momentum. The sum, the total of the two objects, 1 and 2, momentum at the beginning, is equal to the sum of the two objects, 1 and 2, of their momentums at the end. The total momentum at the beginning equals the total momentum at the end. That's saying the same thing as the change in one object's momentum is the opposite of the change in the other. Okay, that's nice. But this is saying the total momentum at the beginning equals the total momentum at the end. This equation we will use many times this chapter. in order to analyze the situation and predict something about final velocities. It's kind of a fun tongue twister too to try to say this out loud. M1v1 initial plus M2v2 initial equals M1v1 final plus M2v2 final. So that'll be a fun thing you can practice at the dinner table and show off with your friends who can say it correctly and the fastest. M1v1 initial plus M2v2 initial equals M1v1 final plus M2v2 final. Good stuff. All right, I'm going to look at my notes and see what's next. We talked about the law of conservation of momentum. And we reviewed F versus X graphs, force versus position graphs, and that the area under the curve was work done. And we talked about the area under the curve here being impulse or change in momentum. Great. And we looked at the beautiful symmetry, and that led us to conservation of momentum. So those are almost all of the things in the notes that we're supposed to talk about today. I have a few minutes to do some example problems now. So we're going to use this law of conservation of momentum. Sometimes I think it's funny to say mv plus mv equals mv plus mv. And of course, it doesn't say a whole lot, so you have to put in the subscripts. You know, one initial, two initial, one final, two final. So we're going to use this law of conservation of momentum to solve some problems. So let's talk about an explosion. Sometimes we have a couple things that are right next to each other and touching. Have you ever been ice skating? I'm starting to think a lot about ice skating because of what season it is. And ice skating is just fun to watch. So let's say we've got two ice skaters on the ice. This ice skater here and this other ice skater here, and they're going to push. So A pushes B and B pushes A. They both start off at rest. So M1, V1 initial is 0 because B1 is 0. And M2, V2 initial is 0 because this initial velocity was 0. So that's kind of an easy left side of the equation. And when the two objects push off, they move away from each other. But do they move away from each other at equal speeds? Well, it depends on their masses. So let's say I've got a 1 kilogram object and a 5 kilogram object. Does the 1 kilogram object push the 5 kilogram object to the right? Yes. Does the 5 kilogram object push the 1 kilogram object to the left? Yes. Do they push with the same number of newtons of force? Yes, they have to because of Newton's third law. What if I tell you that the 5 kilogram object, after they're done pushing, is moving at 3 meters per second? I wonder how fast this guy's going to be moving. The same 3 meters, more than 3 meters per second, faster, or less than 3 meters per second, slower? That would be a great prediction for you to make. And you might even try filling in to the equation here. Take a moment and fill in. If you need to press pause, that's okay. But now I'm going to fill in all the numbers. M1 is 1, V1 initial is 0. M2 is 5, V2 initial is 0. That's 1 times 0 is 0, 5 times 0 is 0. M1 is still 1, the mass hasn't changed, and I want to find V1 final. I want to find this guy's velocity at the end. Plus M2, 5 kilograms, times V2 final. And I'm putting in a positive 3 because the 3 meters per second points to the right. If I get a positive number for V1 final, that means this guy's also moving to the right. Probably not going to happen. So I'm probably going to get a negative number for V1 final, which means this guy's going to be moving to the left. All right, 0 plus 0, 0 on the left. 1 times V1 final is just V1 final plus 15. And look, V1 final is equal to negative 15, which means V1 final equals 15 meters per second to the left. So this minus sign told us what we expected, that V1 at the end is traveling left. Did you predict that V1 would be traveling faster than 3? I hope you did. The little one goes faster. What is this total momentum at the end? 5 times 3 is 15. What is this total momentum at the end? 1 times 15 is 15. So I've got 15 kilogram meters per second of momentum to the right and 15 kilogram meters per second of momentum to the left for a total momentum of 0. Total momentum before was 0. Total momentum after is 0. Negative 15 plus 15 is 0. Momentum is a vector, meaning momentum to the right plus momentum to the left can add up to 0. Energy was not a vector. Energy, which we studied in the last chapter, is a scalar. You cannot have negative energy. You can't have negative kinetic energy. So an object traveling to the right and an object traveling to the left are not going to have a total kinetic energy of 0. So kinetic energy cannot be negative. All right, so that was an example problem. Let me see how I'm doing on time here. Ooh, I have time for one more example problem. Hooray. That makes me happy. Let's talk about a perfectly inelastic collision. Perfectly inelastic. An elastic collision is a collision in which kinetic energy is conserved. That would be worth writing down. Elastic equals kinetic energy conserved. An inelastic collision is a collision in which kinetic energy is not conserved. Elastic is just a synonym for kinetic energy conserved. Therefore, inelastic is a synonym for kinetic energy not conserved. Now, what does perfectly inelastic mean? Perfectly inelastic means the things stick together. So if I have a block at rest, V2 initial equals 0, and I have a block that's moving, V1 initial equals, let's say, 2 meters per second. Let's say that this, let's pick random numbers, 3 kilograms, 4 kilograms. All right, that's my initial conditions. Final condition is they stick together. So they act as one big 7 kilogram block. I've still got my 3 kilograms here. I've still got my 4 kilograms here, but they stick together. So how many final velocities are there? Is there a V1 final and a V2 final? No, there's just V final because they stuck together. It looks like this. He's at rest. This one comes in, bang, they stick together and they move as one. That is what perfectly inelastic means. It means the things stick together. So let's do our work here with our law of conservation of momentum. But V1 final and V2 final are the same number. So I've got M1 V1 initial plus M2 V2 initial equals M1 V1 final plus M2 V2 final, but V1 final and V2 final are the same. It's just V final, which is M1 plus M2 times V final. So what do I have here? I've got M1 is 3, V1 initial is 2, 3 and 2, plus M2, 4 times V2 initial, 0, equals M1 plus M2, 3 plus 4 times V final. Aha. 3 times 2 is 6 plus 0, still 6, equals 7 V final. V final equals 6/7 meters per second. It's positive, so that means to the right. Do you see it? If you don't see it, be sure to ask a question. So that is what perfectly inelastic means. Perfectly inelastic is a wonderful, wonderful, wonderful situation because it's so easy to solve. There's only, instead of V1 final and V2 final, there's just V final, which means I can factor it out. And there's only one unknown. Now, my question is, I told you sticking together is called perfectly inelastic. I'm calling it inelastic. I'm saying right from the beginning, kinetic energy is not conserved. Let's see if kinetic energy is conserved. In other words, 1/2 mv squared plus 1/2 mv squared at the beginning equals 1/2 mv squared at the end. Does it? I don't know. Let's see. 1/2 3 2 squared. That's this guy's kinetic energy at the beginning. Plus 1/2 4 0 squared. That's this one's kinetic energy at the beginning, 0. Does that equal, with a question mark, 1/2 m 7, right, times the velocity 6/7 times 6/7 again, right, 1/2 mv squared. Is the left side equal to the right side? Well, it says inelastic, not elastic. So the answer should be that this and this are not the same. Let's see. This is 0. 2 squared is 4 times 3 is 12. 12 over 2 is 6. I've got 6 joules of kinetic energy at the beginning. And this 7 and this 7 cancel. So I've got 6 times 6 is 36 over 14. Do you see that? 36 over 7 times 2 over 14. I wonder if 36 over 14 equals 6. 36 over 14 joules. Let's look. 36 divided by 14. Nope. 2.57. 6 joules is not equal to 2.57 joules. In fact, there's a lot less energy here. How much less? Sometimes they would say things like, how much energy was lost? Well, then you'd have to subtract that from 6. So I'm going to make it negative and then add it to 6. So we lost 3.43 joules. We lost 3.43 joules. In a perfectly inelastic collision, well, it's inelastic. So of course, the original energy and the final energy will not be the same. And in these collisions, we lose energy. How do you find out how much you lose? You subtract what you have at the end from what you had at the beginning. All right, that's all I have for you today. I hope you've enjoyed. I will see you very soon in class. Have a great day.